A map of the star-forming region in the Orion Nebula, made at mid-infrared wavelengths, gives a picture like this. The yellow and red areas are the places where the strongest infrared emission comes from. These are the protostars. The white contours mark the distribution of cooler, molecular gas. How do these clusters of protostars form? In Chapter 3 we learnt that stars form in dense molecular clouds, and that their formation can be triggered when parts of molecular clouds collide. A team at the University of Wales in Cardiff has been using computers to model molecular cloud collisions. Anthony Whitworth of the Protostar group talked us through the simulation, which results in star clusters remarkably similar to those observed in real life.
Here we see 3 subclouds of a giant molecular cloud, each of about 75 solar masses and about 3 parsecs in diameter, colliding almost simultaneously to produce a dense ridge of gas. The colors here represent how much material there is. Each pixel is colored according to how much mass there is in the column behind it. So the columns with little mass in them are blue, then those with somewhat more mass green, those with even more mass red, and the most massive ones are white. If we look right in the center there, we can see the very dense ridge of gas forming. The density in this ridge is about 10,000 times higher than the density in the original clouds, and the whole collision has taken about 1 million years.
The densities in the central ridge are so much higher than those in the original clouds that we soon run out of colours. So now we'll use the same colours to represent higher densities than in the earlier sequence.
The red gas here is rather denser than the red gas in the first run, where we saw the whole domain. Now the white gas is even denser still, and if we look very carefully we can see the white, very dense gas breaking up into small condensations, and these are individual protostars, rotating disks of gas and dust with masses in the range 2 to 30 solar masses.
Zooming in by another factor of 5 magnifies the picture 15 times relative to the beginning. Again, the densities represented by each colour have been increased.
We can see now about 8 or 10 protostars condensing out here. There's a certain amount of cannibalism goes on here. 1 or 2 of the protostars eat up their neighbours, so we don't end up with quite as many as there are originally. At the end, I think there are about 8. This arrangement of protostars in a long line is very similar to configurations which are seen in molecular line observations of the Orion molecular cloud and the Taurus molecular cloud.
A final zoom in on the filament shows the protostars interacting. The timescale of events here is shorter, a few thousand years rather than 1 million years for the cloud collision. The colours have again been changed to reflect even higher densities.
the densities at the centers of the protostars that form at the end are a factor of 10 to the 9 higher than the densities in the original subclouds that collided at the beginning. We can see two stars, that the top two have merged, or in the process of merging, and the large one at the bottom is also swallowing up some lesser protostars. Each of these protostars that you can see here, we're just isolating a small part of the ridge of protostars. Each of these protostars is a rotating disk supported by rotation in 2 dimensions and by pressure force in the 3rd direction. They have masses in the range 2 to 30 solar masses, diameters in the range from about 200 astronomical units up to about 800 astronomical units.
Now watch through the whole sequence again. This time we'll speed up the action. The end of the simulation might look like a cluster of stars, but there's still a long way to go. Before each is dense enough to begin producing light, there must be a further density increase of 100 billion-fold. Now return to your notes to compare this simulation with observed results. Other simulations by the Cardiff Group suggest that multiple systems are very common in young clusters of stars. This sequence shows the random collision of 20 clouds. We'll speed up this sequence in a few seconds. See if you can follow what's happening. You might like to go back and watch that through again. Well, what was happening? Let's review part of the sequence with Anthony Whitworth.
Observations of very young stars show that almost all of them are at least in binary systems. Many of them are in multiple systems, that's to say they have more than one closely bound companion. What we see happening now is the binary system on the right-hand side is about to merge, so the two stars combine to form a single star, but the binary system on the left-hand side is stable, and by the end of the simulation it's completed 6 orbits, and it's very unlikely to merge. So we end up with a triple system, close binary system on the left-hand side, and then a third star going round in a much wider orbit. And almost all the mass in the region displayed here is in the 3 stars. 80% of the mass is in the 3 stars. So there's very little drag due to the surrounding gas, and so the orbits of these stars are not going to decay. They will remain a triple system, 3 separate stars.